Okay, guys, if you look at this chapter here, I think most of the things you will have seen in chemistry before, like for example, the structure of an atom, where you see that the nucleus, the nucleus is in the middle and it'll have all electrons orbiting around, right? This is something everyone should know by now, right? And then the second thing that you need to know also is the symbol, the element symbol, and what each and every one of the numbers represent. Usually the large alphabet here will be the element symbol. The bottom number will be the proton number, which is the positive charges. The top number here is the nucleon number. What does nucleon number mean, guys? What and what is inside? All right. Jenin told me he was in Thailand. Yes, very good. A nucleon number, it means to say that it has protons and neutrons inside. Very, very important. Everyone must know this. And this one here is essentially going to be the gold-foil experiment. How many of you guys never heard of the gold-foil experiment before? I'm going to take more time to talk about this because arguably this is the relatively more important one. Anyone here never heard of Rutherford's gold-foil experiment or have absolutely no idea what's going on here? Very good. For those who have absolutely no idea what's going on, let me show you a very interesting video. Experiment. Please watch this video. This is very important to help you visualize what's going on. And then I'll tell you all the key points that you need to know later. Watch this video.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil. He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it.
This one was obviously the wrong model, right? Initially, this Thomson guy, he thought that an atom looks something like this, like the jelly thing, the jelly model, right? They say that all the charges are scattered inside, and then it's just like a sphere, which is obviously wrong.
So, Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any. However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees. Based on his observations, Rutherford derived the following conclusions from his gold foil.
What is alpha particle? Alpha particle is actually one of the radioactive what's called radiation that you're going to learn later. There's going to be alpha, beta, and gamma, right? But the characteristics of alpha particle is that it is a positively charged isotope, right? It's a radioactive substance, right? But the key thing is you need to know that alpha particles is positively charged. That's all. By the way, this next part of the video is very, very, very important, guys. Very, very important. Please pay attention to this. I'll explain that to you later, Kunting. Watch this part. It's very important. Pay attention to this. It's literally the most important part here.
Experiment. First, since most alpha particles pass through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point, as a small fraction of particles got deflected completely by 180 degrees, all positive charge and mass of gold atoms are present within a very small volume inside the atom.
Okay, so to reiterate what he said, that this whole experiment, right, was just to prove three specific things only. Okay, three specific things. Number one, the atom, most of the atom is actually made of empty spaces. Why is the atom made of empty spaces? Is because when I shoot positive alpha particles, most of it went directly straight through, indicating that it did not hit anything, thus proving that most of the atom is empty spaces. The second thing he proved that this, you see this blue color line here? When you kind of graze the nucleus a little bit, you see that it suffers a small deflection. Why? This proves that most of the mass is within the nucleus itself. That's why when I shoot the alpha particles onto it, this nucleus will not move because it's very heavy. Instead, the alpha particles get deflected in a very small angle. And the final point is basically going to be this red color line here. The red color line stated that some alpha particles will be rebounded at a very, very large angle. How can the alpha particle be rebounded at very, very large angles? The only way is because most of the mass and the charge is actually located within the nucleus itself. That's why, once again, the nucleus will not move. The alpha particles, when they hit it, it will rebound. It's like basically throwing a basketball to the wall, right? If you think about it, the wall have a much higher mass. Right? That's why the wall won't move. When you throw a basketball to the wall, the ball is the one that rebounds, right? Indicating that this nucleus here has more mass than these alpha particles here. You understand what I'm talking about, guys? Anyone has any questions to this part here? Very important, very important. Good, excellent, 100% absorption rate. That's why I like. And if you look at this statement here, basically these are generally all the things that I've mentioned in a more structured manner, right? Joe has a question. Sure. And if I like throw a ball on the wall like non-stop forever, is there a small chance that the wall will go through the ball will go through the wall? Yes, theoretically it is possible. You know, like when you have water drops that constantly hits the same spot on the concrete floor, over time the water droplet will actually dig into the ground, and then you'll see like a small little hole there, like a small little bore hole there. It's possible, and because every time when the if you think about what's going on, right, like if you think about what's going on, right, like I said, the example of water droplet that constantly drips onto the same spot. If you zoom in onto it, right, you can see that actually what's happening here is the particle is slowly chipping away very, very, very small amounts of particle, right? And every time it drips, it chips away, chips away, drips, chips away, drips, chips away, and drips, chips away. And this story here actually proves that as long as you're determined to do something, it doesn't matter how slow it is. Eventually, even water, which has ideal, right, dripping water, which doesn't, no one feels anything about, they can even dig through these holes. Of course, there's some form of erosion going on as well, right? But the idea is the erosion will be washed away because the water droplet, every time it hits, it splash the particles away, splash the particles away, splash particles away. But this is going to take a very, 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 very long time, obviously. Yeah. But does that answer your question, Joe? Magically go through? No lah, unless Jesus comes down and try to do something funny again. If not, there's no magical experience. Yeah. But that's a good question, Joe. It's a very interesting question. Okay, anyways, if you look at the statements here, these are the things that I've mentioned in a more structured manner, guys. An atom is a complex arrangement of negatively charged electrons arranged in a defined shell. That's why they call the electron shells, right? About a positively charged nucleus. These are the electron shells. This is the positively charged nucleus here. Okay. Then this nucleus contains most of the atom's mass. Most of the atom's mass is inside the nucleus, and is composed of protons and neutrons. Okay, atoms may form positive ions by losing electrons or form negative ions by gaining electrons. Guys, a lot of students have this misconception. If let's say that, okay, right now I want this thing to become positive. What do? Oh, I just add one more proton inside. It doesn't work that way, guys. Why it doesn't work that way is because protons do not move. The only thing that are free to move are the free moving electrons. So if I want this thing to be positive, right, I actually have to remove this electron, then it will become positive, guys. Very important concept, this one here, very important concept, guys. Is there a certain percentage of the atom's total mass that the nucleus occupies, or does it vary? No, most, if not 99%, right, it's going to be like somewhere around 95% of the mass is within the nucleus itself. Okay. Then this part here is very important. This part here always comes out in the exam one. You better know, guys. And the question will look something like this. I will say that, okay, look at this diagram and prove that most of the atom is empty spaces. You're supposed to mention something like, oh, most of the alpha particles pass directly straight through, indicating that most of the atom is made of empty spaces. That's number one. Or they could alternatively, they could ask something like, look at this diagram and prove that most of the mass and the nucleus is within the nucleus itself, right? Which you're supposed to say that it is definitely positively charged because of the deviation from the alpha particles. The positive and the positive, they are kind of like reflecting each other, right? Not reflecting, repelling, sorry. They're repelling each other, right? That's why it will suffer a large deflection or even a small deflection here. And most of the mass is within the nucleus itself, because when alpha particles hit directly on the nucleus, it will actually rebound away, guys. So these are always the key things that you should look out for. Rutherford's gold foil experiment states that atoms have a nucleus which is positively charged, contain most of the mass of the atom, and has space in between each and every one of these atoms here, right? Surrounded by obviously clouds of negatively charged electrons. Most alpha particles pass the atom in a straight direction. This indicates that most of the atom is made of empty spaces, right? Some alpha particles are deflected, indicating that the nucleus is positively charged, right? And some alpha particles deflect more than 90 degrees, indicating that most of the mass is within the is concentrated within the nucleus itself, guys. All right. So this part here is very, very important. You must know. And honestly, these 3 points are relatively more important than the others. Okay. You can jot it down and have a read about it later on. Okay. Then the nucleus is literally just the most basic thing. Like you need to know that this part here is the element symbol. This is the nucleon and this is the proton. Then that's it already. That's okay. Okay. Anyone got any questions for this page here before I move on to the next question? Anyone want to clarify anything that I've mentioned so far with regards to this question here? I mean, this page here. Okay. Good. 100% absorption rate. Just what I like. Then, yeah, this part here is basically just the fundamental things. You definitely learned this in chemistry before, by the way. Tunneling. Oh, wait, tunneling did not chemistry. Right. So, this part here is basically talking about isotopes. Isotopes have a very specific definition. Isotopes are basically elements of the same symbol. That's why they're all HHH, with same proton number, but different neutron number. No neutron, 1 neutron, and 2 neutrons here. In your exam, they love to ask you how to define what an isotope is. the definition for what an isotope is damn straightforward. Literally, isotopes are atoms of the same element containing different number of neutrons but same number of protons. This word here can be interchanged with nucleon number. Nucleons number. Right? Because if you think about it, if I do not have the same amount of nucleon but same amount of proton, this indicates that I have different neutrons also, right? It's just a play of words. It doesn't really matter, but you need to have like this diagram in your head. Like when they ask you what an isotope is, just remember they are all the same element, right? I mean, they don't have the same name, but they're all the same element, right? But they're same proton, but different neutron. Different neutron, different neutron, different neutron. Okay. Oh, by the way, in your exam, they love to ask you this and then they'll give you 2 marks. If they only give you 2 marks, right, then it's very straightforward. Just say same element, different neutron, but same proton, then it's good enough already. But if they give you 3 marks, guys, if they give you 3 marks here, you're supposed to indicate that they have the same chemical properties or same chemical behavior. Having extra protons make atoms heavier, but does not affect their chemical behavior. In other words, they have the same chemical properties, guys. In your exam, if you see like the question has asked you to define what an isotope is, and you see there's only 2 marks, then here is good enough. If there's the 3rd mark, you better say like they have the same chemical properties. Then it's good enough already. Okay, everyone? Anyone's got any questions from this part here? And the final part, which is, in my opinion, the most interesting part. The difference, once again, between nuclear fission and nuclear fusion, guys. Nuclear fission and nuclear fusion always comes up in your exam, guys. And if you want to put it bluntly, right, nuclear fusion only occurs in the sun, and nuclear fission is the one that occurs in the nuclear power plants, the nuclear power plants. Okay, so what's the main difference between fusion and fission? For those who have a hard time understanding, fusion literally means join together, right? Fusing together, right? Fusion, right? So what is actually joining together? They'll have 2 relatively smaller nuclei or nucleus, right? Nuclei. 2 relatively smaller nuclei combining together to form 1 larger nuclei, right? Or nucleus, right? From here, what happens is, right, when they join together, they actually release massive amounts of energy. They release damn a lot of energy, and this energy is actually what is used to power up the sun, basically. If you think about why the sun can continuously burn in empty space for millions, if not billions of years, right? It's simply because nuclear fusion constantly takes space in the sun now. And because it constantly releases a lot of energy, this energy is usually released as heat energy, and thus it starts burning the sun over and over and over and over again. Okay, so nuclear fusion now is the combination of 2 smaller nuclei to form 1 larger nuclei, right? Whereas fission is the exact opposite, guys. If fusion is combination, if fusion is combination, right? Fission is separation, guys. Fission is the separation, and how does the separation occur? So usually if I have 1 nucleus here, right? The first step is to have neutrons bombard onto this nucleus here. And when they are bombarded, right, what happens is they will split into 2. And when they split into 2, they will release byproducts of extra neutrons also. Neutrons also. So when these extra neutrons are free to move about, they will crash into other nucleus, right? It will crash into other nucleuses, and and thus the whole chain process starts repeating. Then this will separate into like one smaller thing and one more neutron, and then this neutron will once again bump into one thing that will separate it into two smaller things, right? And so on and so on and so on. So it keeps happening. It's like a chain reaction, by the way. How do they know what happens in the sun? How they know? Hey, that's actually a very good question. How did they find out nuclear fusion happens in the sun? I've always just accepted the answer, but now you spiked my curiosity. How did scientists discover nuclear fusion? Land on the sun and do live stream? You're trying to be funny, is it, Joe? What is nuclear fusion? What is nuclear fusion? How else? Obviously through observation, but now let me have a look on Google and see what is the real reasoning. When the scientists discover the sun does nuclear fusion, and how did they think it was? The best guess until now was a slowly contracting that was one of the great contributions in the tree. Hmm. Hmm. Can't answer you on that. I guess you'll have to answer. You have to go look a little bit onto YouTube or Google or whatever. But if I were to take a wild guess, I would say they discovered fusion because of observation. Most likely observation. And then they theorized it, and then they must have conducted some small little experiments to prove if their theory was wrong, and then no theory could prove that their theory was wrong. No experiment could prove that their theory was wrong, and thus they just accepted, nuclear fusion. Bang bang. Yeah, but don't take my word for it. I didn't read up enough on that. By the way, guys, when nuclear doesn't matter if it's nuclear fusion or nuclear fission, both of it will release tremendous amounts of energy. But obviously the energy here is actually higher, right? So the question is, if the energy from nuclear fusion is higher, why is Earth only using nuclear fission? Anyone knows the answer to this, by the way? Let's see if you've read enough documentaries or not. Too much energy, not exactly. Anyhow, the energy scarcity is not enough on Earth also. Yes, Kunling, you're correct. Okay, so for those who are wondering why we don't use fusion, even though there's more energy here, it's simply because for nuclear fusion to take place, it has two very specific characteristics. Number one, the temperature must be damn bloody high, for example, or like the sun. And the pressure must be damn bloody high also, for example, in the sun. Today, if we want to recreate nuclear fusion on Earth, we actually can, but the amount of energy that you put in to raise the temperature and raise the pressure, right? Let's say, for example, every 1,000 joules of energy you put in, right? The nuclear fusion occurs and it only gives you 700 joules of energy. This is not going to be power energy production, guys. And if anything, this is energy consumption. And thus, we cannot do that. But for nuclear fission, it's the exact opposite, though. Scientists have already discovered the optimum way, in a sense that I could pump in, obviously it's not going to be for free, right? Yeah, I could pump in like maybe 400 joules of energy. But every time it separates, it actually gives me more energy. So you can see that there's obviously some energy surplus here, right? That's why this here is energy production, and this here is like this energy consumption, and thus we do not use nuclear fusion to generate electricity. Yeah. All right. Anyone's if the process repeats, I assume it will stop eventually. So when does it stop? Good. Nuclear fusion can only occur with the uranium and plutonium sources. So if you imagine how is fire energy generated if we burn a lot of wood, it will be the exact same scenario in uranium and plutonium, right? In order to generate heat energy, we usually burn a lot of wood and then it will convert the chemical energy stored in it into heat energy. Right? Uranium will be the exact same thing also. So the uranium is eventually going to blast and blast and blast and blast and blast and blast. You can imagine like it's a draining battery. Right? Every time it releases energy, it drains its lifespan and its battery, and thus eventually you'll have to replace the uranium core. If not, this is going to be like free energy already, which is obviously not the case. Okay, does that answer your question? Oh, the last part was uranium. Like in order to start a fire, you need logs of wood, right? Right, then you can start the fire. Right? But this fire won't burn forever. What? The fire will burn as long as the wood are still there. Lah. As soon as you finish burning the wood, then it's GG already, no more already, lah. Right? But for uranium, it will be the exact same thing also. Remember, like I told you the energy production process. It could be fossil, it could be coal, it could also be uranium. This uranium is basically used to heat them big pots of water, not pots of water, like some water chamber, and it'll generate steam. And this steam is used to spin the turbine once again, right? And then this turbine will be basically connected to a power generator, which you have learned to be actually just an AC generator, guys. AC power generator. Because every time this thing spins here, it cuts the magnetic field inside here, right? And it'll cut, and eventually it will generate electricity. Okay? Then will the final stages of uranium be just a bunch of protons, electrons, and neutrons scattered? There's no longer. It will be like, it won't be just a bunch of protons and electrons, right? It's not going to disintegrate, but the radioactive part of it is no more, right? If the radioactive part of it is no more, then it could just come out as like a I don't know, like what you see in Simpsons, just like a rod that doesn't glow anymore, right? But exactly how it happens, I'm not sure. I did not look into it deep enough. So the bonds don't break. The bonds for sure break already. Everything will break already. Okay, so if you look at all the things that I've mentioned just now, right now it's just the structured format, guys. The sun's energy is produced through the what? I must be a bit drunk when I type this. The sun's energy is produced by the process of nuclear fusion in its core. Nuclear fusion involves the collision and bonding of hydrogen nuclei to form helium nuclei, right? Releasing nuclear energy in the process. Like I mentioned, this here actually releases damn a lot of energy. Okay, nuclear fission is the exact opposite. A uranium-235 nucleus is struck by a neutron, breaking it into two smaller daughter nuclei and 2 to 3 neutrons, which will once again take part in the chain reaction. And then this whole thing is just gonna go on and on and on and on and on and on and on. Okay? Yeah. So from here, nuclear fission is the process in which a large nuclei are split into 2 smaller nuclei, releasing energy in the process. Fusion is the opposite of that. It involves taking two smaller nuclei and bringing them together to form a bigger nucleus. Okay. Do you guys need to copy this down? Is the box empty? Oh, please copy this down. Very important. Only the box, right? The words are all there. Okay, nice. Copy now. Which one? Oh, this one? Oops. And up also. This one? This one you don't know, man. I copy this one first. Copy this one first. Okay, guys, done copying. Anyone not done copying it? Okay, so Okay, guys, done? Anyone not done copying it? Well, excellent. Yeah, having said that, right? Mm, okay, flip to the next chapter. Let me do a little bit before we end the day today. Actually, no, I'm not going to do anything. Just copy everything. I don't think I have enough time to explain this. Just copy everything from this page first. Next week, when we come back, we're going to just talk about this straight away already, guys. By the way, this was what you wanted to know. The alpha, beta, and gamma is just three forms of radiation in your syllabus, guys. Okay, copy everything down from here, guys, from the next chapter. Then next week, I'll just explain the whole thing and then we'll be done with the radiation physics rate. These boxes are empty, right? It's not written down, right, for you guys. Oh, this is good. Let me know when you guys are done now. Okay, let's do a quick recap of what we learned last week. Okay, guys, are you done copying? For those who are done copying, you can go already. We're not going to proceed with the chapter already. We will talk about this next week, and then oh, oh. Yeah, for those who are not done yet, you can still copy, guys. Yeah, 2 more minutes to copy down everything. Okay, bye bye. For those who are done, you can go already, guys. For those who are not done, you can slowly copy, guys. Don't need to rush. Yeah, for those who are going by, welcome. Bye bye. Welcome. Bye bye. Okay, bye bye. Avish. Okay, bye bye.